greatly enjoyed my previous interactions with Jan at the other festival that he mentioned, and so it was delightful to have a chance to come here and visit an observatory that I've not been to before, and talk to this very interesting and diverse group of people. Before I start, I'm afraid astronomers are very visual, and I've got quite a few slides, so I'm afraid if I could ask people to draw some at least of those curtains. Partway through there's more words and fewer pictures, and you can probably open them again and get a bit of air in, because I realise it's nice to have a bit of air. On my way here, I had the misfortune to lose my baggage. I departed Sydney for Singapore, and my baggage departed Sydney for New Caledonia. I'm not quite sure why. One of the consequences of this was that when I arrived in Singapore, I had to buy myself some new clothes, some new underwear and various other things. And I was intrigued to discover when I opened my little packet of underwear, not only a sign saying who'd inspected it and things like that, but on the back of it was a little motto. And it's a quote from Cicero. It says, "To think is to live." And I thought, how very appropriate for this meeting. To think is to live. I think that certainly applies to this group. But for me as well, and for many of you I'm sure, not only is to think is to live, but to live is to think. Thinking is what I enjoy doing, and so it was a real pleasure to have the opportunity to think about and indeed talk about a topic which I don't normally talk about. Normally I'm doing very much the science of astronomy and cosmology. My particular field is observational cosmology, trying to take a picture of the universe as a whole and trying to relate that to what we understand about Big Bang theory and the like. So it was very nice to think about my thinking for a little while. So this is a result of that, and since this is very much an amateur in the field thinking about his thinking, you'll have to excuse me if some of what I say is well known to you already. But I'm hoping that some of it might be of interest and perhaps even useful and original. So the question that I started off here was, Jan said, well, we're talking about science and technology in the service of beauty and harmony. And I thought about that for a bit. And it occurred to me that, in fact, my own interests and my own thinking, in fact, almost precisely invert that. Not subvert it, just invert it. I'm interested in how beauty and harmony actually serve science and technology. And in particular, to make it more specific, how the concept of scientific beauty serves the scientific method. So scientific methods, scientific theories, models, observations, all sorts of things are commended in the literature or by other scientists as being beautiful. That's a beautiful theory. That observation fits in very harmoniously with the other observations that have come about. A truly profound theorem with great depth, which has radical implications and will be seminal for a new field of thinking. These are all high terms of commendation. This is what you want people writing in your references when you're applying for that job. I want to know what these terms mean, why they have emotional content for scientists, why, more specifically, do researchers actually value those qualities, and, of course, why does any of that matter? If this was just saying, hey, this is great, this is terrific, well, that wouldn't be very interesting. But I think there's much more information in the particular use of these adjectives. Why these adjectives and not some other adjectives? I think it's true. It's certainly true for me, and from my conversations with others, it seems to be true for most, perhaps even all, scientists, and in particular researchers, that there is a tremendous aesthetic component to what they do. They respond to their research not as cold, clear equations or whatever it might be, but with a real sense of beauty. They have an aesthetic response. I love this because it is beautiful. And we find beauty in a range of different things and in a range of different layers. We usually pick our field of research because we find that particular field more beautiful than others. In the same way, the particular problems we address, we pick them because they are interesting, deep, profound, or beautiful problems. And of course, we particularly are looking for beautiful solutions. That's what we are about. We are, to use the word that's been used here very often, passionate about our science. We have a passion for the beauty of it, and we're passionate about achieving something in it, and we love to find beautiful solutions. In fact, you can have two solutions to a problem, and people will say they're both equally true, but this one is beautiful. Why is that solution beautiful and that one not? This is an interesting and I think profound question. So let's just have a brief look at our aesthetic response. It doesn't matter which field of science you're in, whether it's in biology, and I have to apologise for the fact that due to the limitations of PowerPoint and possibly my own imagination, all my examples of beauty are visual, but of course there are people out there, in fact I've got a good friend at the ANU who finds beauty in whale song. They spend all their time listening to whale song because they find that incredibly beautiful, and it's hard to disagree. But PowerPoint, so visual examples. In biology, these are beautiful things. They're not the only beautiful things in biology. For example, if you're an evolutionary biologist, you will find the web of life, the Darwinian evolutionary tree, a beautiful thing as well. If you're an ecologist, you will find beauty in complex systems. If you are in molecular biology, you will find beauty in the subtle code of the double helix. Likewise, you can find beauty in geography, and I gather some of you have been finding beauty in some aspects of that already. Here are some extraordinarily beautiful slices of the geography of the Earth, and it's immediately apparent to all of us that these are indeed beautiful things. But the beauty to the geographer might be much more specific. It will be sharper, it will be better informed and more sophisticated than our response to it, because we don't have the understanding that the geographer has when looking at these rock forms, lakes, whatever the heck these other things are. We all respond with beauty, but their beauty is coming out of understanding. And I think that's, of course, what's so important about science. That's the link, is the link between their aesthetic response and their understanding, and the deepening of that understanding by the aesthetic response and vice versa. Here indeed is some more geography. I think some of you have seen that sort of geography just recently. I'm pretty sure this bottom left geography is entirely photoshopped, since I know that that rock formation is in the middle of Australia, a very long way from the sea. So some beauty can be falsified as well. And then we come to slightly more abstract forms of beauty. So these may be forms of beauty that Jan, for example, finds particularly interesting. These are, in fact, different aspects, different ways of visualising parts of physics. On the top right, we've got one of the big detectors from the CERN Large Hadron Collider. Here we've got a simulation of what that detector might see, and here's an actual set of early results from that detector. And all of these, this is a beautiful piece of technology. This is a beautiful conceptualisation of how fundamental particles react. And this is beautiful because it's one of the events that's the first detection of the Higgs boson. And that over there is just another randomly chosen figure to fill it out, which happens to be a Bose-Einstein condensate. But all of these are beautiful. They're slightly more abstract forms of beauty, and perhaps for the layman, for the person who's not a physicist, who doesn't have the understanding, it's less obvious why they're beautiful, but they are beautiful again. And then finally, at the most abstract level, there's beauty in these sorts of equations. There's some simple basic physics formulas down here on the right. There's a rather joking attempt to write an equation of everything at the top left, which is definitely not beautiful, and even the guy who wrote it commented on that point. But then there are some very beautiful equations down here on the bottom left, Maxwell's equations for the electromagnetic force, and up the top, my own personal favourite, Einstein's field equation. But all of these are abstractions of beauty. This is a way of writing down on paper in simple symbols something that is incredibly beautiful if you understand it. Now, there's nothing beautiful at all about this if you've got no idea what it is. But once you understand it, it is a thing of extraordinary beauty and power. So, let's go from the general to the personal. In my own case, I was drawn to astronomy by two distinct sorts of aesthetic pleasure. One, which is just the simple beauty of the night sky and the things that you can see throughout the universe with telescopes. And for me, that started on the farm that I grew up in northwestern Australia, where I would simply be able to lie on the grass and look up at the sky, and because I was a long way from anything that could be called civilization, I could see the whole night sky in its glory. Because I was living in the southern hemisphere, the centre of the galaxy would pass overhead, the Magellanic Clouds were bright and clear as day, and I just had an enormous, overwhelming aesthetic response to that. But at the same time, I was reading and I was learning mathematics, and I was beginning to see the power and the beauty of the mathematics. And when I realised that you could take the mathematics and describe what I could see in the sky, it was, there's no other word for it, an epiphany. It was a moment when I realised that all of this stuff hung together and that we could understand it. And in the course of my scientific career, I've often, in fact, most of the time, been guided in my choice of field, in the choice of problems that I work on, and even sometimes when I've managed to contribute something in finding the solution to the problem that I seek by that aesthetic sense. I know that other people feel it even more strongly, and some people feel it hardly at all, but I've never yet met a scientist who doesn't have that feeling to some degree or other. So here are some of the things that for me are beautiful. Here's the outworking of Maxwell's equations on the surface of the sun. These are magnetic lines of force made visible on the sun. So these are the lines of magnetic force in the sun's corona connecting different sunspots. Here is a picture of the towards the centre of the Milky Way with the famous Horsehead Nebula with stars being formed. And here it's the complexity of the picture, I think, that appeals to me. It's not a simple thing that I can connect to it, but it is the complexity of what's going on there that I think appeals. It may come as no surprise to you that I'm a great fan of Pieter Bruegel the Elder, amongst others. Here's something that's very beautiful, but again, you really need to know what you're looking at to really understand the beauty of this. These what has been called the pillars of creation, are in fact regions forming stars. You can't see any stars because they're hidden away inside these deep, dusty, dark molecular clouds. But these molecular clouds are being stripped away. In fact, they're not punching upwards out of the bottom. They're actually being pushed downwards and being held together by another star-forming region at the top that's stripping away their surrounds until eventually the cores of those star-forming regions will be exposed. And now we're getting into the realm that I've always found most beautiful. One of my personal favourite equations is the simplification of Einstein's general theory of relativity down to Newton's laws. And this is Newton's laws writ large. This is the Whirlpool galaxy M51. And that beautiful spiral you see there is nothing but the product of matter moving under the influence of Newton's laws. And yet the remarkable thing is, the same is true of this galaxy as well, which looks quite different in many ways, and yet also is largely the product of Newton's laws and a different history of formation. But the thing that I've actually spent much of my career working on is this, and this really does take some understanding in order to see the genuine beauty of it. This is actually the universe in a box. This is an n-body simulation of a very large volume of the universe, where each particle in the simulation represents a very large galaxy, or maybe even a group of galaxies. And the colour coding shows from the darkest yellowy reds down through pink to blue is high densities down to low densities. And what you see, and again, this is purely the outworking of Newton's laws of gravity applied in the context of the Big Bang. And what you're seeing here is the evolution of complexity out of something that was incredibly smooth to begin with. The universe started out with tiny fluctuations at the quantum level, and yet today we see variations in contrast of billions or even hundreds of billions. And even at the scale of galaxies and clusters, we're seeing contrasts at the levels of millions or so. This cosmic web, as it's called, in fact turns out to encode a vast amount of information about the universe. And untangling that code has been what I've spent a lot of my life doing, and I'll come back to that later on. The starting point for that evolutionary model is in fact an observation. This is an observation by the WMAP satellite of the cosmic microwave background radiation. This is the whisper that comes out of the Big Bang, reaching down over 13.8 billion years to today. 300,000 years after the Big Bang, the universe was incredibly hot, it was incredibly smooth. 13.7 billion years later, we see this very lumpy universe where it's very cold. This radiation started out at very high temperatures, hundreds of thousands of degrees at around this time, but dropped to today to just 2.73 degrees above absolute zero. It started out at this time with the fluctuations you can see in the microwave background mapped over the whole sky, only 1 part in 100,000. Whereas today, as I say, we're seeing contrasts of 1 million or more to 1. So that's a factor of 10 to the 11 in contrast over that period. That's an enormous change of evolution, and almost all of that is down to Newton's law of gravity. These are the things I find beautiful, and the reasons that I find them beautiful. So let me try and state again the thesis that I'm going to sort of refine during the course of this talk. The aesthetic reaction of scientists to their profession is a common experience for most, if not all of them. But, amongst other things, and there are many other things you can do with that sense of beauty, I think that the sense of scientific beauty is a scientifically powerful and scientifically effective adaptive response of our intellectual apparatus to a specific fitness problem. The fitness problem of selecting the best world model for the universe, or whichever part of it you happen to be studying, selected amongst a vast array of competing hypotheses and paradigms. And that's why it's valuable to us in our scientific research. It actually has utility. So the sense of scientific beauty is a utilitarian response, a heuristic response, but a utilitarian response to the scientific problem of making models for the world and understanding the world. So I'm going to spend the rest of this talk exploring that notion and trying to refine it. But let me give you a couple of grossly oversimplified examples, and I apologize immediately to all the historians of science in the audience for reducing very complex historical things down to a sort of kiddie's version of them, because I'm trying to make a point. I hope what I'm saying is not untrue, but it's certainly not the whole truth. So, history of astronomy from Ptolemy to Kepler in 3 slides. Ptolemy on the left, Kepler on the right. So, let's think about sense of scientific beauty. Ptolemy invented a system of the world. He was a brilliant man. His Almagest was an extraordinary book that influenced the science for 1,000 years, right? He was by no means a fool. He was a brilliant genius. But he had a fixed idea. He had a particular idea, which was handed down from the Greeks, that spheres and circles were the perfect shapes. And so everything that happened in the heavens had to happen in circles and spheres. So, in particular, planetary orbits must follow uniform circular motion orbits, as that's the most beautiful form of motion. Now, Ptolemy wasn't a fool, and he wasn't blind to observation. He knew perfectly well what the observations were. Admittedly, they were a bit rough and ready in his time, but he didn't ignore them. He wasn't a denier by any means. He looked at the observations, they disagreed, so he adjusted his model. But he didn't adjust his aesthetic assumption. He kept the idea of circular motion and did a whole bunch of other things to his model in order to make it work. And in fact, it worked remarkably well. He introduced, I'm going to bore you with a few things here. For one thing, of course, he's got the Earth at the centre. So he's got the sun going round it. But then on any other planet, and I've picked Mars here at random, he knew that Mars's actual course looked somewhat like the red dotted line. But you couldn't make that on a circle. So what he did was he introduced a deferent, so he offset the circular orbit around the Earth by an equant, which is the point at which this thing makes equal motions. He put the centre of the deferent halfway between the Earth and the equant, and then he added epicycles, so that shown one, but in later versions of the theory there were many, to adjust that motion. So he kept it uniform circular motion at the cost of enormous effort and ingenuity. I mean, this is incredibly clever. I would never have come up with it. So he was trying to save the phenomenon. He was trying to make sure that his theory actually connected with reality, but he had an aesthetic prejudice which led him into this ridiculously complex model. Now, of course, Copernicus made the case for a heliocentric rather than a geocentric system. Tycho Brahe made some much more precise observations of planetary motion, which were a big help in refining the actual data that was worked with. And from those things, from that new theoretical underpinning and the new observations, Kepler inferred 3 new laws of planetary motion and deduced that, in fact, the orbits are ellipses. Now, this cost Kepler enormous effort. If you read histories of it, or even Kepler's own notes on it, you'll see that he struggled with this idea for a long time. Kepler was a very smart man, but he really struggled with this whole idea because he was deeply embedded in the same aesthetic that Ptolemy had. And it took him a great deal of cost and a long time to come up with this much better, much simpler, and as it turns out, much more meaningful version of reality. So, in a nutshell, here's how we go. Ptolemy, Copernicus, we have a new aesthetic. It's a heliocentric system with elliptical orbits is more beautiful than a geocentric system with epoch cycles, etc. Do you agree? Well, I hope you do. I hope that you've updated your own scientific aesthetic to at least the date of Kepler, if not more recent than events. But why do we think that? We think that because it is simpler, because it better accords with the facts, and because it, in fact, is predictive as well. Now, in fact, another oversimplified example, how did we get from Kepler to Newton? Kepler had a fine descriptive model of planetary motion. It was conceptually simpler, it was ultimately more accurate, but it was also just a phenomenological description. He described the orbits, but he couldn't explain the orbits. The limited predictive powers means that they can be applied to other examples. What works for the orbit of Mars can be, with modifications, but minor ones, adjusted to work for the orbit of Jupiter or Saturn. So it had a limited amount of predictive ability, worked for other examples of the same thing, but it didn't deal with new phenomena. And that means it was a weak scientific paradigm. Newton, on the other hand, provided a theory of gravity that was profound and radical precisely because it was a unifying explanation which had predictive power. It could not only explain why Kepler's orbits were in fact elliptical, but it also applied to other phenomena that were not obviously linked to planetary orbits at all, like, for example, the tides. It's not obvious that tides and planetary orbits have at their base a single physical mechanism. That's an enormous conceptual leap forward. So in this case, the concept of beauty wasn't that one idea, circular motion, was replaced with another idea, simplified elliptical motion, but rather that the concept of beauty was extended from one level to another. It was amplified. We kept Kepler's idea of beauty, but then we added a whole nother level. We said not only must the phenomenon be explained in the simplest possible way, but also there must be an underlying explanation for it, which has this predictive power. We made another requirement of a beautiful scientific theory. Okay. Let me shift gears entirely and talk about something which is quite, again, specific to me. It's about an evolving aesthetic sense in response to a new environment. Not a new environment of ideas per se, but literally a new environment. In particular, the adaptation of European artists to the Australian landscape. I think this is really revealing. Initially, the first European colonists who went to Australia, not surprisingly, they were trained mainly in Britain. They tried to depict that environment, which was quite different, in terms of their familiar European tropes and figures. They used the same palette, they used the same idea of what a landscape consisted of. And they put figures in a landscape that looked like English figures. Now, any of you who have ever been to Australia know it does not look like this. Right? This is somewhere in, I don't know, Middlesex, New South Wales. I don't know where it is. It's not any part of Australia I know. These are clearly European attempts to depict Australia. This is Ptolemy. These are epicycles, right? You put a kangaroo in, it's an epicycle in a British landscape. Right? Here's another attempt. Now here, this is another artist. He hasn't fallen victim to that particular problem, but he hasn't really accommodated himself to the environment either. This is sort of the Kepler of Australian painters. Here, he's got, the bush looks right, the colours are sort of right, but the kangaroo is awfully long. It's sort of like a cat that's bouncing around on its own. And I have no idea what this is. I think it's meant to be a palm tree, but I'm not sure. So, again, this is an attempt to adapt to what the world was like. And in many ways, it's a big improvement on what went before. He's picked up the Aborigines as important figures in the landscape. He's noted the importance of fire in the landscape. He's picked up on some quite important ideas, just as Kepler's laws were important. But still, there's something ultimately wrong about it. For those of us who actually live there, it's still not quite right. So, what we've got then is a bunch of rather grotesquely inaccurate and, importantly, unlovely images. For those of us who know Australia, those images aren't right. I react from them. I literally recoil from them. However, as people started to grow up in Australia and a new generation of artists came through, the artists, both individually as artists, evolved, and as a group evolved. And they had new ways of seeing and representing the landscape. And indeed, this now begins to look more like the Australia I know. And in fact, there's a whole nother lecture in showing different ways of doing it. This, of course, is the European way of representing the landscape, which is relevant to my particular point today. But of course, there's a whole nother indigenous way of viewing it, which is the subject for another lecture. The only thing I will mention is that, in fact, these three pictures are done by Europeans of European descent, people born in Australia of European descent. But the one at the top right is by a famous Aboriginal artist, Albert Namatjira. And he's got the best version of the colours. He's the one who's got the colours best at that time. So, these are both more accurate and more beautiful, and the one is linked to the other. These are Australian-born artists with deep personal experience of the country who are able to marry their artistic abilities to a real insight into the landscape. They got it. Okay then, so this evolution of aesthetic understanding is a nice analogy for the gradual adaptation of scientific researchers to the shock of a new discovery or a paradigm shift. So, what happens is, initially, you try and work with the old ideas, you try and work with the old methods, you try and work with your old concept of beauty. And the new fact, or the new paradigm, or whatever it is, seems ugly or discordant. It sticks out in your old picture like a sore thumb. And there's both emotional as well as intellectual misunderstanding. However, over time, again, either individually or collectively, researchers begin to adapt their way of thinking and their perspectives in order to accommodate whatever that novelty might be, whether it be a new observation or a new fact. And as part of that process, their scientific aesthetic changes. And that fresh information is placed into a new ecology of ideas in which it seems natural, right, and proper, and indeed beautiful. And it is often hard to know whether the understanding led to the change in the concept of beauty, or whether the change in the concept of beauty was what fueled the new understanding. So, here's my thesis refined one more time. Beauty and harmony, in the context of science and technology, are heuristic mental constructs that are continually adapted by an evolutionary process to better select true models of the world. Now, the extra word I've added here, which I've sort of hinted at and mentioned a couple of times, and which I would also like to say I was surprised at the absence of in all yesterday's discussions, is evolution. I think that's really important. So I'm going to actually not just develop that thesis itself, but look at that question about how this develops via an evolutionary process. So, the scientific aesthetic, the emotional and heuristic sense of fitness, is evolving in order to function effectively in a new order of things. So here's my off-the-cuff definition of evolution, and I apologise to any biologists in the audience, but I'm going to say that evolution in this very generic sense, not just the purely biological sense, is the adaptive propagation of an entity through feedback involving natural selection. So adaptive propagation, some entity, involving feedback and natural selection. Those are the ingredients of the evolutionary process. In this particular case, the entities I'm talking about are scientific models. The natural selection is experiment, observation, tests, and the feedback is the scientific method itself. So let me try and make this clearer. You start out with some heuristic concept of beauty which is aligned with your current understanding of the world. You apply that beauty measure, as it were, to select new hypotheses. Various ideas come to mind to you, and you choose that one because it's more beautiful in your current way of thinking. You then test that hypothesis, apply the scientific method, and there are two possible outcomes. One is that the new hypothesis is confirmed, your understanding is reinforced, and so your concept of beauty itself is strengthened and enhanced. You give it greater weight. If you want to talk in terms of probabilistic models, it's the Bayesian prior is now stronger for that particular concept of beauty. It's heuristically been enforced. On the other hand, if the test goes the other way and the new hypothesis is rejected, then your understanding has to change. You have to adjust or redefine your concept of beauty and then repeat the process. Now, there are two elements to this that I really want to emphasize very much. The first is, of course, testing your measure of beauty. You've selected a particular hypothesis and then you have to test it. And this, of course, is well known to be at the heart of the scientific method. But I think one bit that's not as well appreciated is that bit in gold over there. When you adjust and redefine your concept of beauty, when you're generating new hypotheses, you have to come up with variants. You have to generate alternative ideas. And that's the really mysterious part that we don't really understand. We have a fairly clear idea about what constitutes a real prediction, what constitutes a test, what constitutes evidence. Philosophers argue about these things, but scientists just tend to get on with them. But a scientist can't tell you, in general, how you do that. It's very individualistic, it's very ad hoc, it's very organic. And I think it's where we need to reform, refine, develop the scientific process. So, again, let me go back to my own particular field and give you a more up-to-date example than Kepler of something that's going on in cosmology. So I like to define cosmology this way, as a subject with deep roots. Started out in the Neolithic, or whenever this chap is, looking up at the heavens saying, where the hell did all that come from? And that's me over there, sitting by my telescope, looking with this incredibly powerful bit of technological kit, enormous cognitive resources at my command, asking the same damn question, perhaps with a little more sophistication. So we now have what we call the standard cosmological model. Again, a little very oversimplified history. Einstein introduces the cosmological constant into the equations of general relativity because he had an aesthetic preference which wasn't that different to Ptolemy's. He had an aesthetic preference for a static, eternal universe. You can see why that's appealing. It's simple, it's straightforward, eternity's nice, stability's nice. Unfortunately, it turned out that not only was it mathematically unstable, it wasn't a good solution, it didn't actually apply to reality because Edwin Hubble promptly went out and showed that the universe was expanding. And Einstein, in response, called it his greatest blunder. Now, today, we've got much more information about all of this. The Big Bang theory holds sway. It's very well attested by any number of different methods. It provides us with an ex nihilo beginning for the universe and a choice of ends. Heat death, if the universe just keeps expanding forever, the heat death is incredibly ill-named because what in fact happens is that everything freezes to death. It's a cold death. The alternative is that the Big Bang turns around, you get a recollapse, and everything ends in a big crunch. Now, within this paradigm, which I've barely sketched, what constitutes a beautiful universe? Well, to narrow this down a little bit, general relativity, as applied to cosmology, relates the energy density of the universe in mass, in energy, and in geometry, in appropriate units, to this very simple equation. These three things had to add up to one. This is a requirement of general relativity. The energy density in matter, the energy density in the cosmological constant, which you can interpret as the energy density in the vacuum, in free space, and omega k, which is in fact the energy density bound up in the curvature of the universe and how the universe is actually bent. Matter and energy tell the universe how to curve. The space-time, the curvature of space-time, tell matter and energy how to move. This is Einstein's general theory of relativity as applied to the universe. So, a beautiful universe, given you've got this constraint, and given that you know that matter exists, I mean, here we are after all, a beautiful universe would say that matter is everything, that omega matter is 1, that there is no cosmological constant, that omega lambda is 0, and that the curvature of the universe is 0 as well. In other words, the universe is geometrically flat, which is a special case as well. That sounds very Ptolemaic, very simple, very appropriate, and just like Ptolemy, completely wrong. This is what we would like to think is a beautiful universe, and what up until the mid-1980s, the theorists all claimed was in fact the case. The matter density has the critical value of unity, there is no cosmological constant, and the universe is geometrically flat. An ugly universe is one where there's no special value for anything. 1, 0, and 0 are clearly special numbers here. An ugly universe would have a critical matter density somewhere between 0, well we know it's not 0 because here we are, and 1, which is the maximum it can be. The cosmological constant would exist, but wouldn't either have 0 or 1 as its special number. And the curvature would be non-zero, it wouldn't be flat, it'd be either positively curved like a ball or negatively curved like a saddle, but it wouldn't have a special value. That would be a really ugly universe. And this was the argument that I heard over and over again from all the theorists until the mid-1980s, when suddenly people realised that, just like Einstein did with Hubble, that they'd been talking through the wrong orifice. So, this is the latest view of the cosmic microwave background. This actually only came out in March this year, so this is literally hot off the press. This is the last word, to date anyway, of our view of one of the most important single clues we get about the universe, that radiation from the Big Bang itself. This is an incredibly beautiful map, and the reason it's incredibly beautiful, which is not obvious, is only apparent if you've got the understanding to view this through the lens of the standard cosmological model. This, the universe has measles. Why is that beautiful? Well, because if you actually try and measure the structure in that pattern of dots, if you try and measure the amount of variation as a function of scale, you get this incredible curve. This is the amount of fluctuation on a given scale. So if you put down a circle on that previous map and say, how big are the fluctuations on average there? That's what you're measuring here. And this is the scale, from large scales on this side to very small scales on that side. The red dots are the measurements from the Planck satellite. The green line is the standard cosmological model. I would say that that is a spectacular agreement between model and data. That is a very complex curve with many features. The best fit model requires 6 parameters. If you try and fit a polynomial to that, you need about 15 to get the same degree of agreement. This is beautiful, beautiful agreement between model and data. Now, in fact, you can do the same thing not at the beginning of the universe in the Big Bang, but right here today. This is work that I've been involved in myself. This is the project that I led to map the local universe. Here we actually went out and measured the positions of nearly 250,000 galaxies in 2 slices through the universe. You can think of this as 2 radar scans, one through the northern hemisphere and one through the south. And the map that I see here is a simplified density distribution of where the galaxies actually are. Here's another version of it, tilted to look face on. Red is dense regions, blue are relatively empty regions. And that map encodes the same structure as the cosmic web I showed you, and is the inheritor of the structure in the Planck map. So rather than, I can do the same analysis, by the way, that the Planck guys did, but let me show it to you a different way. Here on the left is the distribution of the galaxies as we observe them. It's just a mess of dots. On the right, however, are 4 simulated universes. I put in different values of the cosmological parameters, I evolve my universe, and I see what comes up. Now, can anyone tell me which of those universes looks most like the real universe? It's not meant to be hard, it's not meant to be tricky. Look at it and see if you can tell. Who votes for, say, this one over here? No one, okay. How about the top left? No? This one?
No.
Oh, yeah. See, you've got the eye. It's not hard. We all have the sense of beauty, which allows us to map the data to the model. This, in fact, is a standard cosmological model with slightly the wrong parameters, which is why it isn't a perfect match, but close enough. Combining all of that information from Planck, from our redshift surveys, from the work that my colleague Brian Schmidt and others did on the accelerating universe looking at supernovae and so on, we end up with a remarkably precise set of parameters for the universe. And it turns out that omega matter is 0.31, not 0, not 1, but somewhere randomish in between. Omega lambda is 0.61, again, a nothing sort of number. The only number that turns out to be interesting is that the curvature appears to be, as near as we can tell, within the limits of measurement, flat. The universe appears to be geometrically flat. That's the one special thing that survives in this universe. So we have a semi-ugly, semi-beautiful universe. It's neither one thing nor the other. So for me, and I hope for you, this is the sore thumb. This is our concept of beauty now has an ugly spot sitting in the middle. You know, it's a pimple on the face of a beautiful model or something. It's sticking out a mile. This is not right. We have to change our aesthetic concept and our understanding of the universe so that this is the only sensible way for the universe to be. Now, here we have something where the matter density is not critical, the cosmological constant is not 0, and we appear to have something that's geometrically flat or extraordinarily close. In the words of Isidore Rabi, who was talking about the muon, who ordered that? And why? How do we find beauty in this when apparently it is neither well-ordered, something we find it easy to find beauty in, or random, something that also we're actually not bad at finding beauty in? It's somewhere in between. Well, I don't actually have the answer. As I said, this is an evolving question to which we don't have an answer right now. But there are some interesting questions to ask about it in the midst of the crisis. First of all, is there a deep reason that fundamental physics and the parameters of the universe are the way they are, and indeed must be the way they are? Could we find a theory which says it must be so and only thus can it be so? Or, alternatively, do we have to undergo another Copernican displacement, moving us away from the centre of the universe? Do we have to recognise, for example, that our universe is just one instance of a vastly larger multiverse, so that it is not special in any way, just as our Earth is no longer special in any way, and our Sun is no longer special within the galaxy, and our galaxy within the universe, maybe our universe, is just a boring typical universe within some larger multiverse. Will our concept of a beautiful universe change after we gain a deeper intellectual understanding? Or will a more profound aesthetic of some sort lead to that change in understanding? I don't know, but let me just go back to my thesis. Our sense of beauty and harmony in science is a selective adaptation that improves our effectiveness in understanding the world, and these heuristic concepts of beauty and harmony are thus valuable servants in the scientific mind. You've got to nurture them, foster them. Importantly, however, these concepts evolve in the very specific Darwinian sense that they adaptively propagate due to the variation, selection, feedback cycle that is the scientific method. You imagine models for the world, you test the models of the world, and you repeat the process. So, I leave it as an exercise for the reader. Natural evolution is a blind watchmaker. It has no direction. It is undirected. But science involves, at least supposedly, self-aware scientists. The supposedly applies to the self-aware, not the scientists. So in principle, we can direct, or if you're less optimistic, modify the adaptive process itself, i.e. the scientific method, to optimize, or again, to be less optimistic, improve the outcomes we get. How can we attempt to do that? How can we actually change the scientific process to improve this evolutionary adaptation cycle? The things in the process we can change are the selection process, the process of testing models. I'm sure we can improve that, but my personal feeling is that actually we're pretty good at that already. A lot of focus has gone into that. What about variation, the means of generating models? This is where I think we're much weaker. Much less thought has gone into how we generate new variant models of the universe, new aesthetics, in order to come up with good hypotheses to test. And then the final thing we could change is the fitness measure. What actually is a good model? What counts as a scientific explanation? We have been for a long time strongly tied to testability, predictive power, and these are certainly not things we want to get rid of. But it may be that we are reaching the limits of what those can do, at least in some areas, and maybe we need to worry about concepts like plausibility, consistency, weaker, but still relevant ways of saying that this model is better than that model. In conclusion then, I think it's time that we started to apply the scientific method to itself. Can we do better than purely heuristic concepts of beauty and harmony? I leave it with you. Thank you very much.
Thank you so very much.